we should go through example 11.8.9. Is another kind of technique. Uh, but I'll actually do slightly differently. So this is example 11.8.9, but I've changed it a little bit. So originally, this is to calculate this one, CO2, it's 0.1, right? And we did that in another example. And for the case that there's no even symmetry because the integram is an odd function, you cannot refract to a negative real axis to change it, change the integral to minus infinity to infinity. You cannot do that. But we choose another angle is not refract all the way to real axis, but a straight line with the angle 2 pi over 3. Remember that technique. But this kind of integral, that special uh, values of theta, that actually turns out to be okay because it will preserve the same form in the integral. So that kind of a little bit special. And now this example is to use another technique to solve this integral, but it turns out to be that technique becomes much more complicated than this one. And this one actually quite easy that last time we showed. So that is a little bit confusing because why do we do that? If we have a perfectly fine method to solve it and then solve it easier, then why do we go all the trouble to use this method? So that might seem a little bit strange. So I changed it slightly. So instead of doing this, I'll consider this the other integral, x squared plus x plus 1. Okay, so you still break the even symmetry, but without that, we already solved that. So that because without the x term, you have even symmetry, then we can go refract from the to the negative real axis and solve that. But with this extra x, then we cannot do that. So we'll use this technique to solve it. It's okay. So change it slightly. And now this method is not to just change it to compact change x to z and integrate with some contour along the, within the compact z plane. It is not doing that. It's slightly different. And first of all, this obviously this integral is well defined, so from 0 to infinity, and nothing is singular because everything is positive here. And going to infinity is decayed according to 1 over x minus 2, so it's fast enough. So it's well defined. And then if you refract it to real axis, obviously change this. So change x to minus x, but it's still not singular. You can see that the zero of this, the denominator is not on the real axis. But anyway, we'll figure the zero or the poles of the integral later. But what we want to consider is the loop integral of a slightly different function. We basically multiply by a log c function to the integral. Log c dc, c squared plus c plus 1. We'll consider this one a loop integral. And the reason we do that is once you introduce log c, there's a branch point at 0. Then with a branch cut that you choose conveniently, then you can part of the loop becomes this at least proportional to this integral, and then we can figure out the answer that way. And the contour to use is exactly the same as what we did last time. So the contour is not quite good. Here. Let's just go a little bit lower. So there's a branch point at 0, right? And the contour, like last time, is we integrate slightly of the real axis, slightly above the real axis, because we want to cut choose the branch cut from 0 to positive infinity along the real axis. So you go slightly above it, and then you choose a start with a certain delta away from 0, like that. Yes. And then go all the way around the big circle, and then go back to near the origin, and then go a little circle with radius delta, with delta tends to 0 later, and then connect to the upper straight line. So, right? Remember this contour that we did last time? This is I said that you should remember that because it's very commonly used. And the radius of this big circle, of course, is r goes to infinity. The delta goes to 0, r goes to infinity. So this is the contour. Okay, and so give you some names of let's say this is I sub 1. The above from this straight line is I sub 1. This big circle is I infinity, and then below one the I sub 2. The loop around it is I delta. But basically, the same thing, just different path, right? So we define that. So this is like I sub 1 plus I infinity plus I sub 2 plus I delta. Now we figure out the poles of the integram. We exclude the branch point. So the pole is just the 0 of the denominator, which is trivial, right? I mean, you can solve it by this quadratic equation, right? So you see here plus c plus 1 equals 0. So c equals to 1/2 of -1 plus or minus square root of b squared minus 4. B is 1 minus 4 is minus 3 in the square root of I. Right. So this is basically this is just the other two roots of the equation c squared, equation 1. If we solve the roots of c squared equals to 1, that c root 1 is 1, obviously. The other is these two, because if you multiply c minus 1 to this factor, you get c cubed minus 1. Right? You see that this factor times c minus 1 would be c cubed minus 1. So these are the other two roots of the unit circle, which is convenient because so this c would separate 2 pi by 3 equal parts. So this angle is 2 pi over 3. So for a unit circle, the radius is 1. So this is this point, the upper point. This is the lower point, or the complex conjugate of that. And so this one. But we write it in polar form because there's a log. We need to fix the phase angle of this point to get the correct answer. So this is e to the I. By choosing this branch cut, we can choose the range of your polar angle from 0 to 2 pi. So this is obviously 2 pi. We got that's the first one, first 0. So this is equal to e to the I, 2 pi over 3. But for the other one, we keep the theta going. So we will say that this is e to the 4 pi over 3. We will not say this is minus 2 pi over 3, because that would be the other branch. We choose angle from 0 to pi, 2 pi, 0 to 2 pi, so that this one will be I 4 pi to 3. The value are these two, but the phase angle, we need to choose it within this range of the branch. Okay, so that is important. So these are the two poles. So the residue theorem will be, this is 2 pi r. This is the right-hand loop. So it's just 2 pi I times the residues of e to the 2 pi I into 3 plus residue of e to the 4 pi I. Okay, it's okay. You can follow this. All right. Now we argue all these points. So first, easy one obviously. I infinity is 0 because the integrand for all faster than 1 over x. The large circle will be 0. You can accept that. We did that a few times, right? So this is 0. And then the little circle I sub delta is also 0 because we may need to argue a little bit. Because last time I think I went too fast and didn't argue that. So this is over a loop. So you have some kind of d theta. So dc is delta e I theta by d theta. That is dc, and the log c is log delta, and then divided by the denominator. But this is z squares of the order delta square. This is of the order delta. But there's a 1 here, so these two are smaller than 1, much smaller than 1. In the limit of delta goes to 0, this is just 1. Okay, and so you see that this is proportional to delta log delta, and this is tends to 0 in the limit that is goes to 0. The delta times log delta goes to 0. Although that log delta is singular, but it's singular much slower than delta. Right? But much slower than delta goes to 0. Right? So delta times log delta goes to 0. Is that okay? Can you accept that? This is whatever your calculus class. Yeah. Okay. So last time I think that the other example with a log z explicit log z in the integral, right? I forgot to argue that the loop actually need to go around the origin a little bit, but that doesn't change the result because of this result. Log delta times delta goes to 0. So this is 0. Okay, and now so I sub 1, I sub 2. Let's see. I sub 1 is going from integrate for I sub 1 is from delta, which is tends to 0, goes to infinity. Of this is basically this is around the real axis, but we choose phase angle to 0. So log z is just basically log x, right? And then dz is just dx. And the denominator is all single values. Right? So nothing special about that. So log I mean I sub 1 is just basically changing z to x. So the I sub 2 is now it's going back from infinity. Well, let's figure out what the phase angle is. Now phase angle is along this line. So z is r e to the 2 pi I, right? Because the phase is going all the way around. The range is 0 to 2 pi. All right, so we change that. The log z is this is log r plus 2 pi I, and then dz is just dr. And multiplied by this phase factor, but this phase factor will be 1, so that doesn't matter. And the, the again, the denominator is just single value, so that doesn't matter. And but the integral is from infinity to 0, or we can, once we know that, we can flip the sign by introducing minus. Okay, so now you see that this will I sub 1 plus I sub 2, so you need to add these 2, I sub 1 plus I sub 2, both have a similar form, so you have this integral is, this is actually from delta, this is delta, but we'll change, I mean, take the limit, delta goes to 0 anyway, so this will go to 0, because now everything is, we already argued that this, because of that, this is everything well behaved at delta goes to 0, so you can take that limit, and then you see that this I sub 1 cancels with the first term of this one, because there's a minus sign here. This one divided by that integral is the same as this one. So it means that I sub 1 plus I sub 2, and that's the second term, which is minus 2 pi I times this one, right? Because now there's no log x in 2 times n, right? You see that? The introduction of this log z vector is basically so that the two terms cancel between these two, the integral along the upper and lower straight line. So that's like a trick. Once we introduce log, but then these two cancel, but there's extra term due to the change of the phase. And that's minus 2 pi I times the function that we actually want to solve, the integral we want to try to solve. Okay, that's minus 2 pi I times this integral. Now, you need to figure out the residue. I mean, first, of course, you see obvious, there's two terms. Obviously, that's 2 pi I cancel with the 2 pi I. So I is just minus of the sum of the residue. Okay, so that's pretty neat, right? Once you get familiar with that, that becomes a formula. Right? So I is equals to the negative of the sum of this residue. Okay. And now we need to figure out the residues. All right. The residue should be simple, but the residue include a log c, so you need to be careful. Right. So the function that we want to take the residue is log c divided by this factor, which we can change to say log c divided by z minus the two poles. E to the 2 pi I over c minus e to the 4 pi I over c. This is the function, the integral that we want to pick the residues, right? And so there are two poles, and both are simple. So the first one is just multiply by this factor and evaluate z at this pole, right? So so this is the function that we try to do. So this part of we I'm out of space here. Let me just, we already did that. We already did that. The residue. So I is now is minus sum of the residues, Okay. Now the first residue is so there's negative sign minus and log of this. The log of this is a pure phase, exponential of pure phase. So it's just the phase. Log of this is just 2 pi I over 3. And then multiply this factor, cancel this factor, and evaluate z as 2 pi I over 3 minus e to the 4 pi I over 3. That's the first term, and the second term is the same, minus the second is this pole. So you multiply this factor and evaluate everything at 4 pi I, e to the 4 pi I over 3. So the log becomes 4 pi I over 3. And then evaluate C is 4 pi I over 3 is 4 pi I over 3 minus e to the 2 pi I over 3. That's the two terms. Let me see that the denominator actually is the same, but with negative signs. So you can take the common denominator out and change the sign. And the common denominator, you can figure that out. So it's basically this point minus this point. This point, so it's the subtraction of the two roots, right? And this point minus this one, both have the same real part, so cancel the root, but basically just the imaginary part that's right. And I mean, 2 times of the imaginary part, this minus that. This is the upper one, and this is the lower one. So subtract one from the other, cancel the real part. And so that just 2 of the imaginary parts will cancel the 1/2, so it's I times squared of 3. So this is I times squared of 3. So take that out. Take the negative sign out. I times squared of 3. And this becomes 2 pi I over 3 minus 4 pi I over 3. So altogether is minus 2 pi I over 3. Cancel the minus sign, cancel the I. Minus 2 pi over 3. All right, so that's the final answer. It's easier than the textbook one because that one has 3 poles. This only has 2 poles, right? And this answer, you can check that this is an elementary enough that you can look up your integral table or math handbook. So any more comprehensive handbook should cover this kind of integral. And you can look up the answer should be the same. And or you can use your arctangent method to change a variable and the arctangent first complete square of this one and then use arctangent change a variable and you convince yourself this is the same. But the method looks like complicated, but once you are familiar with the techniques, everything is just repeated. So you can much of the step you can just change whatever you know already know because you don't need to argue about this big circle and little circle. You already know that they are 0. So basically, this formula is what you need, and just basically just need to evaluate the residue of the integram and including the log C and figure out all the phase angle and get the answer. Okay, and I mean this is simple enough that you can look it up, but as you can see that can be easily generalized to more factors. So if you have more factor in the denominator, that would be too complicated to look up in the table. But this method is just keep summing the residue as long as the residue is not on the positive u part. If it is on the positive u part, obviously the integral will be singular, so the integral is not well defined. As long as all the poles are somewhere outside the positive real axis, that this method should work. And uh, that becomes straightforward. Yeah. This one is evaluate residue. Whether we want to evaluate residue, right? And the function, the integram we want to calculate the residue is this one. This is from here, right? And you see that they are simple pole because they are first order. So the formula of simple pole is, say, for the first pole, you multiply by the same factor z minus the pole, and that cancels with this first factor. And then the rest you evaluate the limit of the pole. So c change to this one. C change to e to the 2 pi I over 3. So this becomes e to the 2 pi I over 3 minus e to the 4 pi I over 3, which is this one. This is from here, this factor. This factor, which is 1. This one, the numerator. This one.
So the z minus e to the 2 pi over 3, like how does that one go away?
Yeah.
This one.
Yeah, that becomes e power.
Oh yeah, because when you do
this is from the pole. You try to evaluate the residue for this pole, z equals to this one. So the formula is you multiply by z minus the pole, cancel this factor, and the rest you evaluate at z equals to this, right? So c changed to this factor, z changed to e to the 2 pi I over 3 in here, right? And this minus that is this factor. This one, cancel this factor, because that's the formula. That's for a simple pole. The formula, the residue is for at c, say c0, is equals to c minus c at 0 times f c at 0, and take the limit of c. I mean, you can say this is taking the limit, right? Okay. That's fine. Yeah. This, if you cannot follow, just stop me. Okay. Yeah.
Where does the ln or the log z come in again? Like, why do we just insert the log z in there?
This is the trick. This is the trick. The trick. Finally, you realize that in the sum of this I sub 1 and I sub 2, because you see that will cancel. The log will cancel, but not the phase, because because you have a branch cut. Because of the log c is multivariate, go 2 into 2 pi, that introduces extra factor in the phase, extra term in the phase, so that becomes extra term, and then multiply by the rest of the integram without the log. And that is what you want to evaluate. Okay? So the rest, after you cancel the log term, that is the rest. The rest is just I, the original integral you want to do, and multiply by minus 2 pi r. Okay? And so that's basically a trick. But this trick is general enough, because obviously this is just simple power function or fraction function. You can say any function actually that has the finite number of singularity, not including infinity, because later on we want to argue that big circle is 0. So this function that fall off fast enough in the large distance, that would be fine also using this technique, as long as this is single value and not have singularity at infinity. You can generalize this technique to do that also. And because this one you cannot use the other technique. The other technique, you change that from minus infinity to infinity. You cannot do this for this one. This is not even symmetry. It's not an even function. Okay, and then you cannot choose another cut like the x cube plus 1. You can choose another line. That one doesn't work for this one. You don't have another line so that to transform this to exactly the same form. You don't have that. The only line is along the real axis. So we introduce this log z, so that there's multi-value of the integram here. So that introduce the extra factor that get you back to the original integral you want to do. So basically, it's a trick. It's a little bit general trick. Is it okay? Yeah.
And in one of the last questions, 11.8, 8.8,
yeah,
we took I1 as I, but here we are taking this I1.
That doesn't matter as long as the loop integral contains something that you want. Now the loop integral has something that you want as I. Other than the extra factor minus 2 pi, which doesn't matter. You divide it by that anyway. So we divide this 2 pi I from this one. So I is just minus of the sum of residue. So that's fine. Okay, so that doesn't matter. You don't have to always. I mean, this is just a kind of slightly more general method, but also just give you a taste of complex analysis, contour integral. Basically, your imagination is your limit. So it's only limited by your imagination. So you can whatever twist the contour and then introduce other function. So and quite obviously there are many techniques, and if you look at the real complex analysis or complex variable textbook, there are many other techniques or many other problem integral you can solve by it. And then you can do it in research also. So the main idea is not just solve common integral, which you can look up or you put in a computer, but doing it in research. And I did in my research also because I mean, actually, I did a 2 times PhD and another paper. I do quite compact contour integral. My PhD has all these contours. Look at my dissertation. Yes, I twist the contour. All yeah.
Is there any reason why we use R and I2 instead of us?
This one. This one. Why are you out? Just to use the polar form, just not to confuse if the x. X is usually the real part of z. This is the phase with the phase, as you know, is r e to the I theta. Now for this lower branch I sub 2, theta is fixed as 2 pi. Right, so I choose r. But once you figure out that the form of the integral, whether you call this x or r, doesn't matter. Doesn't change the value of the integral. Okay, but this one is you can choose an x because the phase angle is 0. You choose the phase angle is 0. This is purely real, or just this is just z is just the real part. So z change the x. Okay, so whatever name you want to call it doesn't matter. I choose r to make it more explicit that this is the radial coordinate of the z. I choose the polar form. Okay, because we need the polar form to fix the argument. So for whenever you have a multi-value function, you want to use the polar form and fix the phase angle like this pole. If you use you don't fix it and just choose this one, that doesn't work. This one doesn't have a phase angle. If you use this to the final answer, that might not work. You know what I'm saying? So you need, because that doesn't fix the log C factor. The log C factor has a phase. Okay, you need to keep track of this phase of the log C factor over your domain or your interior of your loop integral. That is important because the branch can basically fix your range of your theta angle, the phase angle, and everything within it need to be fixed according to this branch. Yeah.
Yeah. So we have gone up minus 2 pi I, then
Yeah.
I, big I. Then
So yeah.
Then we come to the recipe.
Yeah.
Then we say the log of Z, the one from so we now here are we analyzing for the okay, we take one analytic, one not.
This one within here, within the loop is analytic because within this loop we exclude the branch point. Within this loop, this is analytic except the pole, these 2 poles, and the branch point, but there's no branch point here. So the only two singularity are these 2 poles.
So my question is now we have reached that place.
Yeah.
Okay, after we have 2 pi I.
2 pi I is already here. Yeah, I erased that. The loop integral is equals to 2 pi I times the residue. Equals to this one. But there's 2 pi I here, 2 pi I here. You cancel the 2 pi I. So I is negative of the sum of residues. Okay? Yeah.
I have a quick, sorry.
Yeah, no problem.
Question. How did you get and this is just because my trigonometry is not good in my mind, but how did you get the e to the I 2 pi over 3 and the e to the I?
Yeah, because that's why I argue maybe too quick. This integral, see x squared plus x plus 1, you can multiply x minus 1. Yeah, x plus 1. And that equals x cubed minus 1. You probably can see that because you multiply by x, everything multiplied by x and subtract the same thing. You cancel these two. You can accept the 1, the x cubed minus 1, right? And so this equals 0 means there are 3 roots. One is 1, on the unit circle. The other are the location where you divide the 2 pi by equal parts.
Oh,
So you know that they are of the same unit on the same unit circle, but the locations are at the polar angle that so this is 0, so this must be 2 pi over 2 pi over 3. This must be 4 pi over 3, and there's 3 roots. This is just can you see that? Can you see that? This is when you first learn complex number, you use it to solve equation like that. So the solution of that is x is equals to 1/3, right? The ordinary solution, you can say that it's like that. But with complex number, this is e to the 2 pi I plus 2 pi ni 1/3. Okay, so you have you can say it combines 2 pi ni. So n is 0 is just 1. N is 1 is 2 pi I over 3. N is 2 is 4 pi I over 3. And n equal 4 back to 1 because that means 6 pi I over 3 becomes 2 pi I becomes 1 again. Right? Yeah. So, yeah. Yeah, the branch point is 0. Yeah. The denominator is finite at 0. The denominator is not singular. Because of the log C. Log C has a branch point at 0. We consider this integral. So this integral, the integram has that branch point at 0. Okay.